In this video, we shall look at magnetic fields created by currents in circular loops. In addition to that, we will also look at a system involving current in semicircular loop. Let's look at problem 1. A coil with radius 9 cm carries a current of 5 ampere. We note that this coil is a closely wound coil, so it has a certain amount of turns. The question is, how many turns does it have? If the magnetic field at the center of the coil, that means at this point right there, is 8.38 times 10 to the power minus 4 Tesla. So we start with the expression for Biot-Savart, that is the following formula. The current is I integral of the length vector times r hat, which is the unit vector that goes from the current element to the point of observation, over the distance squared. So this distance is the distance from the current element to the point of observation, in this case that center point there. We note that this coil has n turns, so we should also multiply this expression with the number of turns that signifies the total current. So let's look at a random element of current that makes up this entire coil. The length of this element is, let's say, dl, and the direction of this element, the length element vector, follows the direction of the current, meaning it's going like that, in a direction that is tangential to the point where the length element is. The vector r hat, the direction of that unit vector r hat, goes from the length element to the point of observation. So that is the direction of r hat. The distance from the length element to the point of observation in this case is quite simply the radius of the coil. So it doesn't matter where that tiny element is, let's say here or there or there, the value of little r will always be the same as the radius of the coil. So that expression for the magnetic field can be rewritten in a following manner. R squared. We have taken this term out of that integral because it is quite simply a constant for any such green element around the coil. Of course, now the integral contains the vector dl and r hat. Since this vector is in a direction that is tangent to this point, then this angle must be 90 degrees because this vector is in a radial direction. So when we are concerned with the magnitude of the magnetic field, the above integral will simply become the following, dl. The reason is because this integrand, the magnitude of that integrand is quite simply dl times the magnitude of the unit vector, which is 1, times the angle between the two vectors, which is 90. So sine of that is quite simply 1, so it becomes just that. The integral of dl is simply the length of this entire coil, which is in a circular shape. So that is quite simply 2 pi times the radius of the coil. We note that this 2 pi r will be cancelled by this pi, 1 r there, and this will be 2. So the expression for the magnitude of the magnetic field at the center quite simply becomes mu naught I, number of turns, over 2 times the radius of the coil. Note, we know the magnitude of the magnetic field. That's given by that expression. We know the radius of this coil, which is 9 cm. Mu naught is a constant. The current is 5 ampere, that is also given, so we can solve for the number of turns. Substituting this information, we get the following expression: 8.38 times 10 to the power minus 4 Tesla equals mu naught I is 5 ampere, N is what you want to determine. Divide by 2 times radius, radius is 9 cm, convert that into meter, 0.09 meter, like that. Now we also know mu naught is the permeability of a vacuum, and that is given by 4 pi times 10 to the power minus 7 in SI unit. So substituting this into that, we can solve for the number of turns. And if you do that, you get number of turns equals to 24. So there are 24 turns within this coil. Problem 2. Find the magnitude and direction of the magnetic field at point P. So P is right there, due to the current in the arrangement of wires shown below. The current is 2 amperes. The radius of that semicircular loop is half meter. Of course, there are 3 arrangements, the 3 parts to be considered. The first is that part of that wire that extends all the way from the left to the semicircular loop. Let's call that part 1, and then the arrangement goes into a semicircular pattern, so let's call that 2, and back to a straight segment all the way to the right, so that is the 3rd segment. We note that the left hand side and the right hand side of the arrangement, the wires, are long, so it extends all the way from infinity going to infinity. Of course, the equation to use is the expression for Biot-Savart, mu naught, the current, over 4 pi integral of dl times r hat over r squared. So let's apply this expression to first segment 1 of that arrangement. We note that we have a tiny element with length dl, so that is the length element vector for that straight line segment, and it extends all the way following the direction of the current, so the direction of that length element vector is like that. You see that the angle between the length element vector dl and r hat, which goes from where the current is to the point of observation, is 0. So sine 0 is 0. So the entire integrand goes to 0. So there is no contribution to the magnetic field coming from segment 1 at this point. Now let's look at segment 3. A typical length element vector is like that, so that is dl. And the direction of this dl is going that way, following the direction of the current. Note, the vector r hat for that element is going from where the element is to the point of observation, so that way the angle between them is 180. Again, sine 180 is 0. So also for segment 3, this integrand vanishes identically. So no contribution to magnetic field from segment 3 at the center point P. Now segment 2. Let's assume an arbitrary length element vector is like that. So that is your vector dl. The direction of it is tangential to that point, and it makes an angle of course 90 degrees with respect to vector r hat. So that's 90 degrees right there. So the expression for the magnetic field due to segment 2 at point P will be mu naught I 4 pi. The distance of a length element, doesn't matter where it is, whether it's here or here or here or here, to the point P is always the same as the radius of that semicircular loop. So this little r is quite simply constant and taken out of that integral, and you get that expression. Again, the magnitude of this integrand is quite simply dl, and the integral of that is the length of that semicircular loop, which is pi times the radius of that semicircular loop. So first we can compute the magnitude of the magnetic field. It is mu naught I over 4 pi r squared. The integral becomes pi times the radius. We note pi r cancels this pi and that r, giving you the expression mu naught I over 4 times r for the magnitude of the magnetic field. Substituting the constants, so the constant mu naught is 4 pi times 10 to the power minus 7 in SI unit. The current is 2 ampere over 4 times the radius is half meter. So you see that this will cancel that, giving you a magnitude for the magnetic field to the amount of 4 pi times 10 to the power minus 7 Tesla at point P. Now let's determine the direction of the magnetic field at point P created by that segment 2. So to see how that works, let's assume the length element is here. So the length element, the direction of that current is that way, so that is the direction of the length element vector. This is the direction of r hat. So you see in the expression for the magnetic field, you have a term like that. So as you cross with your right hand fingers from this vector to that vector, your thumb is pointing into the plane, like that. So the direction of the magnetic field is actually going into the board. Let's see if the vector element, the current element, is there. So that is your current element, like that. So the direction of that current element is that way. The direction of r hat is that way. So when you perform this cross product from dl to r hat with your right hand fingers, your thumb is again going into the board as concluded earlier. So it doesn't matter where you place the current element or which current element you choose along this segment 2, the result of the cross product between the length element vector dl and unit vector r hat will always result in a vector that points into the plane at point P. So to conclude, the magnetic field at point P has a magnitude of 4 pi times 10 to the power minus 7 Tesla in the direction into the plane.